Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. To go through some fundamentals, really as far as to really how these parts work, how they function, and really some of the different topologies of how they how you make them, and really the trade-offs and advantages of one topology over another. All things are not created equal. Some are better than others for certain applications. We'll talk briefly about some applications, and then go through really what differentiates TRM from some of our competitors.
Thank you, Shaun. And maybe next you could define couplers in a more technical way compared to that simple definition that I'd given a little earlier.
Sure. So really a directional coupler is a device and that samples signal coming off of a line. It couples energy. And in that respect, by the word couple, meaning it could actually theoretically mean almost any coupling value, although in this definition, it usually means a small sample. You're coupling just a little bit of the energy offer there. And by directional, it means that it only picks up energy flowing in one direction on the line. I think the thing that's important about this is that if you were to have a sampling device that was that coupled energy in both directions, that would be like a resistive kind of type of a network that would actually give you the same energy regardless of the direction that's flowing on the device. A directional coupler will only sample energy flowing in one direction. The thing to keep in mind also is that the hybrid we talked about in the last session are actually just a special case of a directional coupler. They couple energy in only in one direction as well, but it's a special case where the through line and the sample power are equal. So that's the case of a hybrid. A directional coupler is a case where the sampled port is much lower in amplitude than the energy flowing on the main line.
Okay, well, that was good to clarify. And maybe you could also clarify a little bit about the multi-port nature of directional couplers. What's that all about?
Yeah, sure. So couplers are by definition a 3-port device. We actually have an input and an output on a through line. You think about some type of transmission line going straight through there. Basically a through coaxial line just going straight through, input and output. And then we have the third port, which is where the energy gets coupled off to, that output port that has a little bit of energy going to it. Now, by nature, and the way that these parts are designed, there is a fourth port. The fourth port is internal to the directional coupler, and that energy is used to balance the network. What makes what actually makes these parts directional is the fact that it only samples in one direction. The measurement of energy flowing in the opposite direction we refer to that as directivity, and that helps identify the quality of the coupler. It's a parameter that we test for and we specify in all of our sheets. So how well does the coupler reject energy flowing in the opposite direction? Like I said, that's a qualitative measure that describes how well the coupler is working, and it is something that we definitely tune and design for. So really, it's a 3-port device. energy goes through in the forward direction, and a small part of that energy gets coupled back out to the coupled port. Energy flowing in the opposite direction gets rejected, and just basically just goes straight through the unit.
Okay, got it. Thank you. I've also heard you refer to dual directional couplers. Can you explain that, please?
Absolutely. So dual directional couplers are really two directional couplers in the same package. There are multiple ways to do this, but basically what you do is you have two directional couplers, one facing forward, the other facing in the reverse direction. The forward coupler picks up energy and samples energy going in one direction. And the reverse coupler picks up energy going in the opposite direction. So this way here, you actually have two separate devices inside of a package. Very often, if for certain measurements, you want to sample in both directions, depending on your particular application. For example, if you want to measure the amount of power coming out of an amplifier, you want to have energy coupled up on the forward direction. And if you want to see, for example, what the VSWR of your load is, and how much energy is being reflected back to the amplifier, a reverse sample line would do that as well. Therefore, you can get both the forward power and the reflected power coming back from your load measured via the same device. This is a very popular application for directional couplers. This is just to validate how much energy is going down the line and how much energy is being reflected back into the source.
Okay. Now, are dual directional couplers different from bidirectional couplers?
Yes. Now, a dual directional coupler are truly two separate devices in the same package. A bidirectional coupler is literally just a single coupler, but that internal termination that I spoke about earlier is brought out as a separate port. So what you have here now is you can sample energy in both directions with a bidirectional coupler, which means that you can get one port will sample in the forward direction. The output port will sample in the reverse direction, but there is virtually no isolation between those two sampled ports. A dual directional coupler has those two output sample ports for forward and reverse direction are isolated. In a bidirectional coupler, they are not isolated at all. It is a single wire going through the device and coming back out again. So for certain applications, again, this can be useful. It is far less popular to build a bidirectional coupler because of the fact that the two outputs are not isolated from each other.
Yeah, so now I can see this is going to ultimately lead us to some of the nuances associated with what you and your team has to do when deciding which is the right one. But I'm also under the impression that there are other types of couplers too. And I've heard you talk about lumped element couplers. Maybe you could explain the difference there.
Sure. Now, going away from the generic kind of what is a coupler, we're now getting involved to how do we actually make these, and by making these this way, we can accentuate some of the properties of some of the technology, and going forward there. All couplers, all directional couplers, work off of the fact that if you have a varying electromagnetic field, that if a wire or a transmission line is sitting in close proximity to the line that the wire is going down, it will induce a current in the opposite direction in that wire that is in proximity to it. So the simplest example of that that's how transformers work. Transformers have a primary and a secondary. The primary has voltage running through it. An electromagnetic field expands and contracts. That field crosses the secondary and induces a voltage in the secondary windings. That is exactly how a lumped element directional coupler functions. These are wire wound transformers. We use ferrite beads to help concentrate the magnetic field. And this is how the sampling happens. We have a wire that runs directly through the transformer as a primary. Then we have a secondary winding that's wound on the transformer where that energy couples back off of to sample the power. The diagram on the screen is a very simple broadband lumped element coupler that TRM builds. This particular one works fairly low in frequency, works down to about 20 megahertz and works up to about a gigahertz. That's sort of the range of the ferrite technology as far as how it likes to go. So this is really in the lower frequency megahertz. These things have typically very broad bandwidths. The bandwidths can be up to like 100 to 1. So very broad band, very good performance, low loss, and these parts are quite efficient from a size standpoint, because really we're winding transformers, and therefore we can make them quite small, depending on the power level required.
Okay. Now, how about strip line couplers? Maybe you could speak about those a little bit, please.
Okay, so the next version, once you get away from a true wire wound transformer, thinking about a power transformer that you plug in, for example, to charge your cell phone, using the same idea is that you can print a line in on a PC board, have a line that is in close proximity to that line, and the same function happens is that the electromagnetic field expands and contracts and induces a current in the line that is running next to it. We do this in strip line, and what happens here is that these couplers with a single transmission line that is a quarter wave long, these work very efficient at building a coupler that has about an octave's worth of bandwidth. Two examples on the screen here. The one on the top is one for a tighter coupled coupler. The two traces are on opposite sides of the PCB, so that those transmission lines can get closer to each other. Once we get to looser couplers, the one on the top, for example, is a 10 dB coupler. The one on the bottom is a 20 dB coupler. And as you can see, the lines are getting farther and farther apart, and therefore less energy is coupled over into the adjacent line, because the wires are getting farther and farther apart, and the magnetic field is getting reduced as you know, for that field to cross that secondary line. These parts over here work very good. These are really set up for frequencies in the gigahertz range. Sometimes you can into the high megahertz use this technology, and really that comes back to the fact that you need at least a quarter wavelength long of line to be able to build a coupler using this technology. A quarter wavelength line at 30 megahertz, for example, is roughly 9 feet long, which makes it impractical to go ahead and build a 9-foot long line to be able to build a coupler using this technology. The difference, if you get up to 10 gigahertz, for example, a quarter wavelength line is about 1/4 of an inch, which makes a very nice compact sort of structure. So the technology here really, from a frequency standpoint, is limited more by physical size than by theory. But this is a very good performing technology. Like I said, in a single quarter wavelength line, has about an octave's worth of bandwidth, works great for the higher gigahertz type frequencies.
Okay. And did I also understand that couplers can have more than one section within internally? I guess I'm not clear on that. Maybe you could talk about sections.
Sure. So this is the next part that we're starting to get a little bit confusing. The last discussion was talking about a single quarter wave section giving you an octave bandwidth. Very often we need more than an octave worth of bandwidth. How do we do that? By superimposing multiple sections, we can mathematically build a power series that has a broader bandwidth than the single coupled section. Basically, if you go through this, some of the ideas of Chebyshev tapers and how they're realized by using a power series, you can realize that you can add multiple quarter wavelength sections along with varying coupling values, and when you add them all together, you end up with an equal ripple function that can be over a very broad band. The example, for example, on the top here, the longer tapered asymmetrical taper on this one over here has roughly a 9-to-1 bandwidth. That one there is one way of realizing this. Another way of doing this is using a symmetrical taper. The one in the lower right, for example, also has a 9-to-1 bandwidth, but that is a symmetrical taper with a smoothing function between the individual sections, as opposed to the one on the top, which actually uses a almost digital type of a step function in there. The coupler on the lower right is a 3-section symmetrical design that has roughly a 3-to-1 bandwidth. So by varying the number of sections and the way that we go with either a symmetrical design or an asymmetrical design, we can vary the bandwidth and also vary the performance by paying attention to the way we transition between the sections. And these are really just some really high examples of really how we manage to get good performance over very broad bands. Very high frequencies, for example, do not like digital steps. And that's why the design in the lower right very often is more applicable to very high frequencies, whereas the one that's up on the top with the steps on it very often are used for kind of the mid-range frequencies. And that's just a matter of trying to go through them, trying to optimize directivity for these sorts of structures. There's a lot of detail that gets involved in designing these. They are by no means simple to design, but we're quite successful doing it here at TRM. And this is just one example of how we expand the bandwidth of an individual coupler.
Okay, and you mentioned taper a few times, and I understand there's also a tapered line coupler, correct?
Yes, there is. And this one over here now shows the previous examples are all examples of bandpass structures. The mathematical function behind those is based on a Chebyshev function, which is a bandpass structure. This particular example here is based on a high-pass structure, which means that this mathematical function has a low-end cutoff, which is equal to some multiple wavelengths of the length of the line. And depending on the elliptical function that you use to generate this, the length is going to vary as far as where the low end goes. Topic for another talk. But basically, this will continue to operate higher and higher frequencies, and essentially has no theoretical upper limit mathematically. What limits the upper limit on this in reality has to do with whether or not the cavity that this is put into, so we don't generate higher order modes in the cavity or have some other kind of crosstalk between the connectors, the cavity, and the strip line. These are ultra broadband as far as the way that these are actually realized. Tremendous bandwidths are available for these sorts of structures. Kind of the downfall of these sorts of structures is they want to be fairly a significant portion of a wavelength at its lower frequency, and that's what determines the low end cutoff of these frequencies. So in order to build a coupler, for example, that's going to work, say your need is to work, say 1 to 10 gigahertz. A stepped coupler will probably end up being at least half the size of a tapered line for that same low end, for that kind of a bandwidth of having, say, a 9-to-1 bandwidth. If you need a bandwidth operating at, say, 15 or 20 to 1, then actually the tapered line will then actually be shorter, because the number of sections that you would need to add to the asymmetrical tapered line, the asymmetrical stepped line, would be so high that line would actually start becoming longer than the tapered line. So when you start talking about ultra wide bandwidths, there's a trade-off between the overall physical length of the device versus the bandwidth. And at some point, a tapered line begins to win that battle, and that's when we start talking about developing tapered lines as opposed to an asymmetrical stepped line.
Okay, well, that all sounds good. And maybe you could provide just a few more details on how these various types of couplers are actually used.
Sure. So a big piece of how couplers are used is monitoring the outputs of amplifiers. Basically, every amplifier needs to understand, the system needs to understand how much power is being broadcast out. So very often at the output of an amplifier, you will see a directional coupler, both to sample the forward direction, as well as how much energy is being reflected back. In those cases, you will very often have different coupling values in a single dual directional coupler. It is not uncommon, for example, for a high power amplifier to have a 40 dB coupler going forward, making sure we have a reasonable amount of power coupled back from the transmitter. But because the reflected energy is so much lower, maybe you want to have a 20 dB coupler, for example, on the reflected side of that dual directional coupler. So therefore, you'll have two separate couplers that are truly independent of each other with different coupling values depending on the application. Another thing that we use directional couplers for quite frequently, if we want to inject a test signal, for example, onto a main line without having to unhook cables or connectors. Very often for injecting other test signals or calibration signals onto a transmission line, you can not only couple energy from the main line to the coupled port. If you put energy into the coupled port, it will come out on the main line, and that's a very nice way to go back and to inject a signal onto a main line. Also, if you have to mix a very a high power main line, and you want to inject a low signal signal on top of that, without having to incur the combining loss on the main line, you certainly can go through there and use a directional coupler for that. You have the high power on the main line of the directional coupler, and the lower power signal comes in through the coupled port. They both add together, and they both come out of what is not what we would ordinarily refer to as the input of the coupler in that case. So a lot of applications where you're trying to either take a small signal off of a main line and sample it, or inject a signal onto a line for later analysis going down the line, either for calibration or some other measurement, an injection point for a measurement.
Okay, well, that makes sense. So maybe tell us a little bit about what's special about the way that TRM adapts these couplers.
Excuse me. Yeah, I mean, one big thing, of course, that TRM does is that we build these products using a wide variety of technologies. There is no one technology that is better than any other. For example, if you're looking at a lower frequency sort of part, then you're going to want to use a wire wound ferrite-based sort of technology. Getting up to higher frequencies, you're going to want to have a strip line sort of technology. One of the advantages is of course that TRM uses all of these sort of technologies, with the exception of waveguide, to be able to build these devices.
Okay, and I think in the past we've talked about this too, but I suspect that screening and validation is involved as well.
It is. It's a big part of what TRM does, and it's a value-added service. Many of our customers realize and are very happy to say we pay for paper, which is all the testing and validation. It's not always just the hardware, and we're happy to do that for our customers, to validate our parts, make sure that they perform well in their system. Okay, and how about packaging? And again, the packaging is another big part of what makes a custom part. If a particular application has a mounting strut in the way, very often things that are structural for an aircraft, for example, need to be there, and it just so happens that a connector on a device is for a normal layout wants to be in the same place. Those very often we can help the engineer solve those problems by moving a connector, changing mounting surfaces, doing some relayouts and those sorts of things. So that sort of custom packaging really goes a long way with our customers as well. Well, thank you, Shaun. I think you've shared a lot of good information about the couplers, about how they're used, and about some of the things, once again, that TRM needs to do to make them fit the right applications. So maybe you'd like to just summarize the session? Sure. I mean, basically, what directional couplers do is they take energy off of a main line and allow you to sample that energy. That goes back into whatever feedback loop that you have for an amplifier, leveling loops. Sometimes you just want to sample amount of energy, whether you're dealing with some radar applications, to make sure that the encoding is going correctly, all those sorts of things. they actually, and they're very useful because they only sample energy in one direction, and energy or reflected energy that's coming back on that line will not be sampled. Dual directional couplers are basically just two devices in one package, and therefore the outputs for those are isolated from each other because they are separate devices. Bidirectional couplers, basically we're just removing the termination from one line, so they will function on some level like a dual directional, but there's no isolation between the two outputs. Certain applications, those can be okay. Other places, not so. That does pose a problem because those two outputs are not isolated from each other.
Excellent, excellent. And before we answer a couple of questions, once again, it just becomes very clear as I'm listening to you that while technically TRM Microwave sells components and products, it's really the collaboration, the sharing of ideas, and the customization that makes the big difference in how successful these devices are once they fit into wherever it is that they're headed. So from a question perspective, we do have one here that the question is, do printed directional couplers have to be strip line, or can they also be microstrip?
That's a good question, and I didn't really mention it as we were going through the conversation. All of the printed couplers that I had in this presentation were strip line, and really the big trouble with having a microstrip coupler is the fact that microstrip is a non-TEM mode propagation as opposed to strip line, which is. So what that means in layman's terms is that a microstrip coupler, the velocity of energy going down that line is not linear across frequency. There's a dispersion that happens. As a result, because of that dispersion, you cannot build a physical structure that will have the same electrical length, whether we're talking about the even mode or the odd mode. A little complicated there, but really what there's energy that is flowing down the main line, and then there's energy that is flowing across to build a magnetic field to couple the energy across. Since those two modes are not exactly the same in a microstrip sort of structure, you will not get full cancelization for directivity in the reverse mode. So what that means is a microstrip coupler, although it will work in quotes in a forward direction, will have very poor directivity by nature, and there's really not much you can do about it. You can tune it a little bit if you're dealing with a very narrow band coupler, but for any sort of appreciable bandwidth, because of this nature of the propagation, it's virtually impossible to get a good performing directional coupler in microstrip. Therefore, these parts, we always design these in strip line because basically being a true TEM mode, we can get all those velocities to align, and therefore we get good directivity.
Okay, well, thank you, Shaun. And I think to stay within our timeline, we will address additional questions through email after the fact. If you are a customer and you have additional questions, please contact our engineering group directly using the hotline number that's on your screen, 888-677-6877. If you are one of our field representatives, certainly you can call the hotline, but you can deal directly through your CAM and also find recordings of this and other Tech Talks on the field representative portal. So our next tutorial is going to be in mid to late March. We have not identified the specific topic as of yet, but the first series that we've completed today now covered each of the four major categories of the components that TRM manufactures. So we will begin to drill down into more detailed uses as we go forward. Thank you all so much for joining us, and thank you, Shaun.
Yeah, thank you, Paul.